So, good afternoon, everyone. So today is the last day of our final of our short-term course, Current Research Trends in Civil Engineering. Uh, so the topic of my presentation is Bazant Le Kirane Paradox of fatigue fracture. Uh, I just want to bring the attention, so I'm calling it as the Holy Grail of Mechanics. So we'll discuss about the fatigue fracture using Paris law approach, and then how the Paris law approach was used to study fatigue in concrete and other causal brittle materials. That also we'll discuss in today's lecture. So, one minute. Some people are there. Yeah, sorry for that. So then we'll discuss about fatigue fracture for concrete and how the Paris law approach was used to study fatigue fracture. And then I will highlight the paradox has uh, which I identified in the studies. So in the first slide, we have I'll give a brief introduction to the quasi-brittle fracture mechanics, which is applicable to materials like concrete and glass fiber composites, bone, ice, and lot of other materials. So here in this picture, you see a specimen, test specimen, which is loaded in tensile direction, and this specimen has a small sharp crack inside it. So when when the load in the specimen is increased, what happens is at the crack tip, micro cracks starts to form, and these micro cracks grow in size as the load increases. So in quasi brittle materials, this zone of micro cracking is large, and it can be comparable to the size of the structure. These micro cracking, what can happen is here there can be interface breakages or void formation or frictional slip between the aggregate and cement paste. So all these are all these can put together as micro cracks or micro cracks, and uh, these large zone of micro cracking is also called as fracture process zone. So all the fracture processes which are happening at the crack tip, and the zone is called as fracture process zone or denoted as FPZ. So this fracture process zone is a unique characteristic of causal brittle materials. So as I was saying, concrete, fiber composites, bone, ice, and also epoxy resins toughened with carbon nanotubes or epoxy resins toughened with nano alumina. All come under this causal brittle fracture. We can uh, the manifestation of this causal brittle fracture mechanics. The main application is that the strength we observe a strength dependency, size dependency of on strength, and also we observe a size dependency on the fracture toughness. So what happens exactly at the crack tip is as the micro cracking happens, the ability of the material to take further load in this region is diminished. So if you plot the stress along this ligament, what we see is this blue line. So blue line indicates that the stress capacity is reduced. So initially the stress capacity is sigma y, and after that, when the further cracking happens, the ability to take load is reduced, and as a result, the value is dropping down. The stress value is dropping down in this region of softening. So with this basic introduction, I will go ahead and describe the way to quantify this size of the fracture process zone. So one of the most widely used equation in quasi-brittle fracture mechanics is this Bazant size effect equation, which was developed in 1983 by Professor Jednek Bazant at Northwestern University. So he has come up with a size effect testing methodology to, I think some people are there online. Yeah, we add them. Yeah, I'll come. There are some more people who are trying to join, so I'm trying to add them. Sorry for the. I think I have added two people, so Karthika and Sandra. So size effect testing was proposed by Professor Bajang, and he using that size effect testing, we can characterize the quasi-brittle fracture in concrete and other materials. So the description of size effect testing is shown in brief here. What we have is a test specimen, and this test specimen is loaded under 3-point bending. So we are having support here and here, and there is a point load applied at the midspan. So this test specimen has already a small crack, sharp crack at the center. The size of this crack length is A. The distance between the span length is L, and the depth of the beam is D. So in this size effect testing, what we do is we maintain the ratio of A by D and L by D constant. That means uh, that is the specimen can be geometrically scaled, keeping these ratios constants A by D and L by D. So A is to L is to D, that proportion is kept constant throughout the testing. And we do tests for at least 3 specimens of different geometrical sizes. So we have here specimen size D1, specimen size D2, specimen size D3. And these specimen sizes are scaled in factor of like 1 is to 2 is to 4, or it can be higher also, 1 is to 2 is to 4 is to 8. If it is possible to test a 8 size specimen with a scaling of 8. So we cast specimens which are geometrically scaled, and the ratio can be, as I was saying, 1 is to 2 is to 3 is to 4, 1 is to 2 is to 4, and more also. So for each specimen, we measure the load versus deflection curve. So we apply the load P, and then we calculate the deflection. And the load versus deflection curve was shown for the 3 sizes here, D1, D2, D3. So we have here for smaller size, the peak load is PU1, and as the size is for size D2, we have peak load PU2, and size D3, we have peak load PU3. And after peak load is reached, we see a drop in the load value. That means the material has softened, that it is not able to take as much load as at the peak. Okay. So the strength carrying capacity has reduced beyond the after the peak load after peak load has reached, the strength carrying capacity is reduced. Now using this peak load values, we can calculate the strength of the structure using this formula. Sigma is C times PU by BD. C is a geometric constant depending on the loading and the geometry. So for 3-point bending, it will be, I think, 3 by 2 BD, 3 by 2 D, and it will be like 3 PU by BD square, something like that. So the strength value. So once we get the strength values, we can use this size effect equation. It's proposed by Professor Bajant. It's called the Bajant size effect equation now, and it is of this form. Sigma nu is BFT by square root of 1 plus D by D naught. So in this, the experimental, excuse me. So in this equation, the values obtained from the experiment are, so you can treat this like the x value. You can treat this like sigma nu value and d value are the given parameters, and you have to find the unknown BFT and d naught. Okay. So for the set of data, so sigma u1 d1, sigma u2 d2, sigma u3 d3. for those three set of data, we can plot, we can find the BFT and BFT and D naught values. So we are plotting it on a log scale here. So we have log sigma by sigma naught and log D by D naught. So BFT is rewritten as sigma naught. So what we have here is, for very small sizes, that means in this range, very small size, this D value is very small and sigma value will be equal to sigma naught. So we have a strength criteria here, sigma equal to sigma naught for small sizes. And as the size of the structure increases, what happens is the D by D naught value will become larger and larger, and its value can be far greater than 1. And as a result, for very large size, the sigma value is inversely proportional to 1 by square root D. So in that case, so as the size increases, the strength will decrease, and we see this line. Okay, this line with a slope of 1 by 2. So when you write in log scale, log sigma will be minus of log D. So minus of is the slope for this line. So there is a transition in the strength. There is a transition in the load carrying capacity from the strength criteria to the LEFM, or the linear elastic fraction mechanics criteria. And we can identify sigma U1 D1, sigma U2 DU2, sigma U3 D3 here. So the smallest size specimen has larger strength, and as a size increases, the strength is dropping, and the largest size, which is D3, has the smallest strength. Okay, so this is the Bazant size effect equation. You can write it in this form, or you can write it in this form. But the main take home point is there are two lines. One is a horizontal plateau, and there is the LEFM line, and the strength is transitioning from this strength criteria to this linear elastic fraction mechanics criteria. So D naught is a transition length from strength criteria to is a parameter which will dictate the transition from strength criteria to LEFM criteria. So the only way to calculate D naught is by experimental work. Only when you do the experimentation, then only we can calculate D naught. There is no theoretical way or no analytical way to solve to know D naught without experimentation. Okay. So once we do experiments, then only we can calculate this D naught value. So yeah, this is the regarding the size effect testing methodology. And I will go ahead with one more equation for fracture toughness. So in fracture mechanics, we come across this term fracture toughness. It is it is calculated as the failure load times the stress intensity factor. Stress intensity factor can be rewritten in this form: square root of d k naught a naught by d. And if you substitute the Bazant size effect values, sigma nu, replace it with BFT by square root of 1 plus d naught, you can rewrite this in this form. So d by d naught, you can replace it with a term called beta, and you get something like this. KAC is KAF square root of beta by square root of 1 plus beta. So what we are having is a size dependent fracture toughness. So fracture toughness is depending on the, it depends on the size of the structure which is tested. Okay, so this formula is applicable for quasi-brittle materials, and we will be using again this fracture toughness this formulation when you study the Paris law in the coming few slides. So this Bazant size effect equation was originally proposed in 1983, and at Northwestern University, a lot of experimental work was done to support that formulation, and the people have tested different materials, and they found that size effect equation was applicable to all those materials they tested. And after the civil engineering community, it initially was skeptical about using the size effect equation. They were trying to they were not sure whether to put it in the building design codes or not. But what happened after a lot of ASA committee was formed. The committee number is 209, and they worked with the civil engineering community, and then they convinced them to incorporate the size effect equations in the building codes. So finally, after a uh, lot of struggle, the boson size effect equation was incorporated in the ACI 318 American Concrete Institute Building Code 31819, which was 19 it represents the year and 318 is the building code. So where is it incorporated in this code? It is incorporated in the shear design. So ACI 319 introduced a new set of simplified equations for one-way shear strength, and this is applicable to non-precious beams, slabs, and walls loaded out of plane. The equations include a size effect for sections that do not have minimum shear reinforcement. So only for this sections where minimum shear reinforcement is not there, the size effect equation was proposed. The size effect is also applicable to two-way shear and to strut capacity for strut and tie models without a minimum grid of reinforcement. So this is another place where they have uh, proposed the incorporation of the size effect equation. The size effect factor is not applicable to isolated and combined footings. So the size effect factor is given in this form. Lambda s is square root of 2 by 1 plus t by 10, which I will discuss in more detail in the next few slides. So in the original shear design for ACI code, they have proposed this shear strength for non-precious members without axial force. So, and also they have this formula 2 lambda square root of f prime c bd. And for precious members with axial compression and non-precious members with axial pre-compression, they have proposed some formula like this. And for axial tension also, they have proposed this formula. In the ACI 319 code, they have proposed this size effect factor lambda s. Yeah, I was saying 209. It's actually ACI company 446 which has proposed this. And this form, if you see the lambda s factor, it is square root of 2 by 1 plus d by 10. It is similar to the boson size effect equation. So we have a parameter of 10 here. So this parameter 10 is kind of probably it's like the d naught, which is the transitional size, which is in the boson size effect equation, and this parameter is proportional to the maximum size of the aggregate used. And we can see that as a d is the depth of the member. As the depth of the member increases, the lambda s factor will reduce. Okay. So the strength capacity of the structure is reducing with the size of the structure. Okay, as size increases, the strength is reducing. So that size effect is incorporated in the ACI 31819 code. Okay. So all this was based on this boson size effect equation, and I'll just show where the factor is. It is lambda s here. Wherever the Whenever the shear reinforcement is less than the minimum required, there we use this equation, and in this equation we have our lambda s parameter. So that value is this lambda s parameter. Okay, so for non-precious members with reinforcement which is less than the shear reinforcement, there we are using this lambda s parameter. So this is regarding the boson size of it equation and its incorporation in the ASA codes. Now all these derivations and all the testing was done for monotonic loads, and the parameter d naught was also obtained through the monotonic loading. Monotonic loading means the loading is increasing from 0 to the peak load. Okay, let me just turn on the camera if possible. So yeah, monotonic loading means the loading is increasing from 0 to the maximum load in a like constantly increasing. There is no oscillation and all. Okay. But usually in structures, we see that there is not only monotonic loading, there is also cyclic loading. Cyclic loading means like if you have a bridge and what happens is a vehicle passes over the bridge. So if you take any point on the bridge, what happens when the vehicle is passing, the load on that element will increase, and as the vehicle passes over, the load will drop down. So this load which is the element is experiencing is not the peak load. Means the material is not failing. It is well below the failure load. Okay. So this type of, again another vehicle comes, again the load will increase, and once the vehicle passes, the load will drop. So there is a lot of load cycle, repeated load cycles acting on a structure in real life. Okay. So for example, a bridge, or if you are sitting on a chair, if you are sitting on the chair, what happens is when you're sitting on the chair, there is some load, and when you get up, that load is gone. And the chair is not failing. The load is well below the failure load. Okay. So this type of loading is repeated loading, and failures can happen even for repeated loads well below the peak load. So although the peak load is not reached, if you have sufficient number of cycles of these loads, the material can fail. So this type of failure is called fatigue fracture. Okay. So to understand fatigue fracture, people have come up with some tools. One of the tool is called Paris law, and another tool is SN curve, which I will not discuss in this presentation. So we'll discuss about Paris law because we are interested in the crack and the crack growth and all. So it is relevant. So I will discuss about Paris law, and then how Paris law is used for quasi-brittle materials, and what are the modifications to the Paris law for quasi-brittle materials, and how it introduces a contradiction, how it introduces a paradox. The experimental work introduces uh, uh, two different conclusions. So what is that? What are the two different conclusions, and why is that a paradox? So that I will highlight in the next few slides. So yeah, so we have the Paris law. So Paris law was initially used for design of metal components in the aerospace industry, especially in aircraft structures. So aircraft structures had a lot of uh, there were some spectacular failures in the early 1950s where some airplanes exploded in midair. So they try to understand why it is happening, and they figured out that it is due to the crack growth happening in the interior of the aircraft structure. The cracks are not visible, but under repeated loadings, these cracks are growing, and when the cracks reach a critical size, then the structure itself is failing. So if this happens in the air, then the aircraft will fail, and loss of lives have occurred. So people have studied that, and they have come up ways to quantify the number of cycles the structure can take using this Paris law approach. So this Paris law has been used for design of aircraft components, and we are trying to and civil engineering community have also looked into this quasi-brittle fracture in the quasi-brittle materials like concrete. So people have studied normal strength concrete, high strength concrete using the size effect methodology. To, so what they found is that unlike the metal components where the Paris law parameters are independent of structure size, they have found this Paris law in quasi-brittle materials. The Paris law components are dependent on size. So in the last decade, like in 2014, some tests were done on barrier sandstone and somewhat tests were done on concrete, and they were also used to study the Paris law, and a modified Paris law was proposed. Okay, so I will tell you how to calculate how to determine the Paris law in the next few slides. So so the first step in the Paris law approach is we will identify the loading. Suppose we are doing a tensile loading test. What we do is before going ahead with the test, we do a FEM simulation. So in the FEM simulation, we model the test geometry, and then since we are applying a tensile load here, we are applying a tensile load here with a small crack. Only certain half of this geometry is modeled in this FEM model. So we are taking half of the model. We have this crack A naught, and we have this tensile load acting on this edge. So for this, in this FEM model, what we calculate is we calculate the displacement or the stretch in the material divided by the applied force. So we are calculating the stretch. So for this case, there will be stretch in this direction here. On the mirror image, there will be stretch U naught. So the total stretch will be 2 U naught. And 2 U naught divided by the applied load will calculate. And this value is called compliance. Okay. So for this crack length, we calculate the stretch divided by the applied load. That is, we calculate the compliance for this crack length. So this is the C compliance, and A is a crack length. A is a crack length. So for different A value, we find out the compliance using the FEM simulations. So we calculate the C of A for different A, and we keep it aside. Then we go ahead with the applying the cyclic load on this structure. So the cyclic load is applied in this fashion. First, we do a normal test and we apply the load. And once the peak load is reached, the material will fail. We find out what is the ultimate load. That is the peak load value we'll find out. That is under a monotonic loading test. So we are increasing the load constantly and peak load is reached. So we calculate sigma u. So this sigma u is determined. The next step is we operate, we apply stress on the structure well below the sigma u. Okay. So we identified a range. So sigma minimum, sigma maximum. So sigma minimum can be like 5% of sigma u to 8% of sigma u. And sigma maximum can be 70% of sigma u to 80% of sigma u. So what we do is we apply a cyclic load. So initially cyclic tension load. So initially load is 0. Then we apply load up to 80% or 70% of sigma u. Then again reduce the load to 5% or 8% of sigma u. And then we again increase the load to sigma max and then reduce the load to sigma minimum. So we keep repeating this load cycle. Okay. So this load cycle is repeated. So we load it, unload it, load it, unload it. So this is repeated. And at one point, so during the loading process, what will happen? Some cracks will start to grow. And at one point, at a particular end cycle, the structure will fail. So this is the fatigue test, which is done in laboratory. So from this fatigue test, we find this n value. We also have these two parameters, sigma max, sigma minimum, and we have the crack length A, and we have a stress intensity factor and all, which we can obtain from the SIF handbooks. So we are now introducing a term called rate of fatigue crack growth. That means rate at which the crack is growing. It's not a time rate used is not, in this case, is not dA by dt, it's dA by dN. dA means the increase in the crack length by dN. dN is the cycle number. Okay. So every cycle, in each cycle, the crack is growing little amount. So what is the rate at which the crack length is growing per cycle? Okay. So that is what is determined in the Paris law. So rate of fatigue crack growth, it is based on, and what they found is this dA by dN is dependent on the stress intensity factor range. Okay. So stress intensity factor is a common terminology used in fracture mechanics. So let's discuss that. So we have K max, that is a maximum stress intensity factor, which is given as sigma max square root of pi a f of a by d. So this is obtained from f of a by d can be obtained from the SIF handbooks. And K minimum is sigma minimum, which is square root of pi a f of a by d. So the stress intensity factor range is delta K, which is K max minus K minimum. And from this we get stress intensity factor delta K, stress intensity factor range delta Ks, sigma max minus sigma minimum is delta sigma times square root of pi a f of a by d. So what this thing is saying is that the rate of crack growth dA by dN is dependent on delta K. Okay. So let's go ahead and do the analysis. So what you're doing here, you are applying the cyclic load. So during the cyclic load, we are recording the load versus deflection curve that is shown here. So the load versus deflection curve. So initially in the load cycle 1, we have initially load is 0 when increasing the load, and then we are unloading it. It is coming down here. So as you keep doing this load cycling, what happens is the crack will start to grow, and micro cracks are formed, and crack will start to grow. When the micro cracks are formed, the stiffness of the structure will reduce. That means if you have the low deflection curve, initially it will be like this, and as crack starts to grow, the low deflection curve will become smaller. The slope will become smaller and smaller. Okay, so we have large slope here, and as the test progresses, the slope is getting reduced. Okay, so the slope is getting reduced, or if you take the inverse of the slope, what will happen to the inverse of the slope? Inverse of the slope should increase. Okay, if the slope is getting reduced, slope of this low deflection curve is getting reduced, the inverse of the slope will increase. Okay, so the inverse of the slope is also called the compliance. So delta by P is called the compliance. So as the slope is getting reduced, the inverse of the slope will increase, and that is the compliance value will keep increasing. That means the material we can stretch more and more easily with the progression of the crack. So what we do here is we measure the compliance, that is the inverse of the slope for cycle 1. So suppose we get compliance for cycle 1 to be somewhere here. Then we get from the FEM simulations, we get the compliance curve. We had the compliance curve. We already determined the compliance curve. So we go in this in the right direction, hit the point in the curve, and then we go downward and calculate the corresponding A, that is the crack length. So using this low deflection curve, what we can do? We can calculate the inverse of the slope, that is the compliance, and from the compliance, we can calculate the crack length. Okay. So for each cycle, we calculate the compliance value, experimental value, and from that, that using the FEM curve, which we have already done, we calculate the corresponding crack length. So this we do for each cycle. So cycle 1, cycle 2, or we can do in steps of 100. Cycle 1, cycle 100, cycle 200, like that. And as you keep repeating it, we get the compliance and the crack length. So cycle 1, crack length is A1. Cycle 100, crack length is A100. Cycle 4000, crack length is A4000. So what we can do is we can plot the cycle number versus crack length. Okay. So cycle number is shown on the x-axis and the crack length is shown on the y-axis here. So initially the crack length is A, and as cycles are increasing, the crack length is increasing. Okay. So we get this crack length versus cycle curve for a stress range delta sigma 1. Suppose if you repeat this test for a different stress range. So if you change this is the stress range, sigma max minus sigma minimum. If you increase the stress range, so if you change the sigma max, keep it little higher, or if you reduce the sigma minimum a little lower, then the stress range will be increased. So in that case, what happens is, if you do the experiment again, for a higher stress range, we can expect the crack growth to grow more rapidly. Okay. So what is happening? For the same cycle, the crack length is higher here for the higher stress range. So if you plot, if you see here, crack length is some A, and if you go to the next curve, the crack length is still higher. So here the rate of crack growth is increased when the stress range, that is delta sigma, is increased. Okay. So we can repeat this experiment for different sigma delta sigma values. So we'll get multiple crack length versus cycle curves for each delta sigma. Okay. Now we have to work with this data. First thing is we'll take one curve and get some data like this. So we had our crack length versus cycle curve. For a crack length A, we calculate this slope dA by dN, and we also calculate for this A the stress intensity factor range delta Ka, which is given by this formula delta sigma square root of pi a f of A by d. Okay, so we get a set of points like this. We get dA by dN and delta K for a delta sigma, for a given delta sigma. Okay, so we get multiple points, 1, 2, 3, 4, 5, 6, like that, dA by dN and delta K. Okay. So for a given stress range, we can get a set of data points, delta K, dA by dN. Now we can change the stress range. We can increase the band of the stress range, or we can reduce the band of the stress range, and we get another set of data points, delta K J dA J by dN. So we can repeat this for multiple stress ranges. Okay. And once we are done with this, we can plot this delta K and dA by dN values. So delta K we plot on the x-axis and dA by dN we plot on the y-axis. Okay. So that's what we are doing here. So we have delta K here and delta dA by dN on the y-axis. So we are plotting it in a log scale. And so initial set of points are like this, delta K dA by dN for one stress range delta sigma. So another stress range we calculate the delta K dA by dN and we plot it. So we can repeat it multiple times. And what they have found is experimental work what done on metals. What they found is all these extra all these data are found in a single cluster of points like this, and these cluster of points can be fit by a line. Okay, and they have identified three regions in this line. So this is region 1, this is region 2, and this is region 3. So region 1 indicates very slow growth of crack. So the crack growth is very slow. It is around 10 power minus 8 meters per cycle in this region. And in the intermediate region 2, the crack growth is little higher. It's around 10 power minus 8 to 10 power 5 meters per cycle. And in the third region, the crack growth is shooting up. It is rapid crack growth is happening, and it is above 10 power minus 5 meter per cycle. So in the second region, they have identified a almost straight line. Okay. The straight line is on the log scale. So we have a constant slope here. So log dA by dN is equal to that is y is equal to mx plus c. Mx plus c, yeah. So log dA by dN is equal to m c log dA by dN will be c log c plus m log delta k for this line, which if you rewrite in normal terms, it will be dA by dN is c delta k power m. Okay. So if you take the logarithm, it will be log dA by dN is equal to log c plus m log delta k. So log c is the intercept of this line, log intercept, and m will be the slope of this line. Okay. So this is the Paris law, which was originally obtained for metals. And this Paris law parameters are the c and m value. Okay. They have thought that these c and m values are unique to the material. Now, the same approach, uh, which was done for Paris law, which was done for metals, is now repeated for uh, was uh, was applied to quasi-brittle materials. That is, for example, concrete. So Basant and Zhu, they first pioneered the studies in understanding fracture in concrete through the Paris law approach. So what they did, they studied concrete beams under 3-point bending. So they have they have two supports and they're applying load here in this direction. And they have tested uh, three geometrically similar size specimens. The depths of the beams are D1 38, 76, 152 millimeters. The scaling is 1 is to 2 is to 4. So 38 into 2, 76, 76 into 2, 152. So 1, 2, 4. So this size is twice this size. D2 is twice D1. D3 is 4 times D1. Okay, so this is a geometric scaling. A by D is kept constant. A by D is 1 by 6. L by D is also constant. It is 2.5. So initially they did a monotonic loading test. They carried out a monotonic loading test and they found the sigma U1, sigma U2, sigma U3. And after that, they did a cyclic loading test. So cyclic loading, once you know the maximum values which the beam can take, then they cycle it lesser to a value lower than that peak value. So in this case, they have tested ranges from 0 to 0.80% of the maximum load. So they cycled over this range. So initially load will be 0, then it will increase to 80% of maximum load, then reduce to 0, and again increase to 80% of maximum load. So like that, they have repeated the cycles and done a cyclic loading test. So cyclic loading tests were done for all these three different sizes. And what they found is they have used the Paris law, they have got all the data, and then they use the Paris law approach to plot the log dA by dN and log del K. Okay. Log del K on the y-axis, x-axis, and log dA by dN on the y-axis. Okay. So they have plotted this. And what they found is, so they have three different curves. So for size D1, this is the curve. Size D2, this is the curve, and size D3, this is the curve. So the Paris law slope is same for the three sizes. Okay, exponent n, there is almost same. There's not much uh, difference is there, but the intercept value is different. Okay, so we can say that this Paris law parameter C is size dependent. Okay, so what they have tried is they have tried to modify this fracture toughness and introduce a size dependent fracture toughness. So earlier I have shown that equation Ks is Kf square root of beta by square root of 1 plus beta. So instead of using Ki, instead of using Kf, they have used Kic. Okay, in the size in this Paris law output. So instead of Kac, they put Kf. So if you substitute, what you get is, yeah, instead of, sorry, Kf, they use this size dependent fracture toughness. And if you substitute it, you will get an equation like this. dA by dN is C delta K by Kf d plus d naught by d. And they have tried to see how the curves are. So using this modification to the Paris law, that is introducing this d naught parameter, the curves initially which were far away, got little closer. So then they thought this again they are not able to get a single line, which should be a they should just try to get a single line, but they're not getting using this approach. So they hypothesize something like this. So they introduce something called a parameter DOC. Okay, DOC. So this is the new length scale which they have introduced, and this length scale accounts for the transition from small size to linear elastic fraction mechanism criteria. Just like in the monotonic size effect, we have D naught, where the transition from strength criteria to LFM criteria is happening. Similarly, for cyclic loading, they are introducing this parameter D naught C, and this parameter gives a transition from the small size to LFM criteria. Okay. So again, using this modification, instead of B is D by D naught, they are using beta is D by D naught C. So the Paris law equation is modified with KAC as KF d plus D naught C by D. Now what they did is they varied the values of D naught C, and they found that at D naught C is 10 D naught, all the three curves merge together into one single line. Okay. So this is the value D naught C, which is 10 D naught. All the three curves are merging together. Initially, they had this wide curves. Now all the three are merging into one. So they have come up with this idea that T naught C is the transition length, and D naught C is assumed to denote the transition of Paris law from small size specimens where the fracture forces shown at the crack tip is comparable to the structure size to large size specimen where FPG is negligible compared to the structure size. So what they got is D naught C is greater than D naught. That means the specimens are more brittle under Oh, okay. This is difficult to understand. I think it's more brittle under monotonic loading than cyclic loading because I should have that curve by the side. So yeah, that is another thing we can get. Yeah. So these were one set of experiments which were first done on concrete to quantify Paris law to get a estimate of the Paris law parameters and all for causal brittle materials. Then another set of experiments were done on sandstone in around in the last decade, 2014. They have done some tests on sandstone. There are many more tests done, but I'm showing some of the main experiments. So again, these were 3-point bend tests. Unlike concrete, what they use is instead of concrete, they are using sandstone, Beria sandstone. Okay. So the scaling is again L by D is 2.5 and A by D is 0.2, and the size of the structure was scaled from 1:2:4. So we have smaller size 25.4 depth and larger size 101.6. Again, they did all that cyclic monotonic loading test. Then they found the peak load. Then they did the cyclic loading test from 0 to some percentage of the peak load. And then they got all the data. Then they analyzed all the data. And then they plotted this dA by dN versus delta K. So again, they found three distinct set of points. So this is for size 25.4, this is for size 50.8, and that is for size 101.6. So for each size, all the data can be fit by almost a straight line. So what they found is this, again, the slope is almost close, 19, 17, 22, but the y-intercepts are far different. Okay. So Professor La, who is at University of Minnesota, so he has come up with fracture at nanoscale. So he has looked into this what cracking at a nanoscale level. So what he has hypothesized is that we have the crack tip, and at the crack tip there is a cyclic fracture procedure. And if you take a small micro crack and zoom in on that, so this is a small micro crack, and you are zooming on that, and this micro crack itself have smaller size micro cracks, and these micro cracks are at the nanoscale level. So at the nanoscale level, we're looking at the atoms and molecules. So some crack propagation is happening at the nanoscale level. So he equated the energy of the crack crack formation at the nanoscale, and that energy is equated to the energy dissipated at the macro scale. And he also used some activation energy theory and rate process theories to define crack growth at the nanoscale level. Again, it is a theory which is used to fit the data. Okay, so they have this dA by dN at the nanoscale, and delta K is the stress intensity factor at the nanoscale. So it's just a theory which was used at the nanoscale with the molecules and all. So, so using a stress intensity factor nanoscale is it's a novel concept which they have tried here. Okay, so the main take home from this fatigue from this is that they're trying to relate the fatigue fracture energy uh, over the different sizes. Okay, so just like fracture energy for monotonic loading, we are using this equation GF is GF infinity d by d plus d naught m. For fatigue fracture energy, they are come up with this equation. UC is UC infinity d by d plus d naught c. So using this formulation, they finally do some mathematical algebra, and then they get this term. Delta KD is delta K 1 plus D naught C by D whole power of, which is similar to what was obtained by Professor Bazant in his first pioneering research. So this is the crack growth, dA by dN, rate of crack growth, and that is equal to C delta K power n D plus D naught C by D whole power n. So again, they have found a parameter D naught C, which is 1.5 times D naught, the monotonic size. And using that, all the three set of data which were identified here, they cluster into one single set of line. Okay. So using this modification, they are able to cluster all these 3 experimental data into a single line. So this is the modification they have proposed. And another thing they have done is they have looked into the digital image correlation and acoustic imaging to understand how the crack growth is happening here in monotonic loading and how the crack growth is happening in the cyclic loading. So the main conclusions from that is that they have identified the tip of the traction-free crack coincide with the zero displacement jump across the crack ligament. So that means uh, at the crack tip, if there is opening, that means one node is moving to the left, another node is moving to the right. That means there is a displacement jump happening, okay, in the DAC study. So using this, what they have found is something like this. Okay, digital correlation image study for monotonic loading. For monotonic loading, what happens is the crack growth is happening, the traction-free crack is formed, and the FPG size is moving with the crack tip. Okay, so this is happening simultaneously. The crack tip is opening, and the FPG size is moving with the crack tip. So this is what they found in the monotonic loading. In the cyclic loading, they didn't see this. When the load cycles are being applied, instead of the crack tip moving ahead, the crack tip is staying where it is. Okay, and only the size of the fracture post zone is increasing. So this is a phenomena they observed it during DAC study. So the crack is not growing, but the size of the macro cracks are increasing under cyclic loading. Okay, so only FPG size was increasing. The length of the traction-free crack remains constant up to this much loading cycle. Okay, as at when the loading cycle reached 20,500, then onwards the crack started to grow. Okay, so this is what they observed, and the size of this FPG in the cyclic loading is around 1.5 times the monotonic fracture process zone size. Okay, so this is what they have observed experimentally from the DAC study also. Uh, this result, if you keep in mind, and if you look at another test, which set of tests which are done on concrete, they found a completely opposite conclusion. Okay, so they have done a 3-point bending test under monotonic loading and a cyclic loading, and then they have got this DA by DN curves for small, medium, and large specimens, and they have fit some lines, and then they have collapsed all those lines into a single line using this delta KD is delta K1 plus D naught C, this using this equation. Okay, and they have identified this D naught C parameter, and this D naught C parameter is smaller than D naught value. It is around 0.5, something like that, 0.5 D naught. Okay, so so this is the another slide where we look into what is happening at the under monotonic loading. So in monotonic loading, what they found is the crack tip is moving forward. The fracture process zone is also moving with the crack tip. So the zone of micro cracking is moving with the crack tip. For cyclic loading, what they found is under cyclic loading, the fracture process zone size is very small, smaller than the monotonic loading size, monotonic loading fracture process zone, and it is growing right from the beginning. Okay, so this is a completely different result from what was done by Dr. La, Professor La on Berrios sandstone. Okay, so what they have found is that, so the contradiction is like this. So what Dr. La has found, Professor La has found is that under cyclic loading, the FPG size is increasing, and once it reaches a critical size, which is larger than the monotonic fracture position size, and then it started to grow. And the traction-free crack started to grow. This is what was observed. In this experimental work by Kirane et al., what they've seen is that the size of the fracture post zone, that is a zone of micro cracking, is smaller than the fracture forces shown under monotonic loading, and the cyclic fracture force zone travels with the traction free crack right from the beginning. Okay, right from the beginning of the uh, 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 like during the loading process, the cyclic FPG is traveling with the traction free crack. Unlike the first case where the FPG size grows and then at certain high number of load cycle, at a very high load cycle, the crack has started to increase in size. It has to grow. Okay, so this is the paradox which I have identified from this analysis. So to summarize, this is the summary. We have our monotonic fracture process zone size, which was identified by Law et al., and there is a cyclic fracture process zone size. So according to Law, the monotonic fracture process zone size is smaller than the cyclic fracture process zone size. So the fracture process size is around, cyclic fracture is 1.5 times monotonic fracture zone size. But according to Kirane, the monotonic fracture process size is greater than the cyclic fracture process. So it's opposite. Okay. So this is what I call as the Bazant Le Kirane paradox. So Professor Bazant was the PhD guide of Law and Kirane, and he was a pioneer in the possibility materials. So I'm call this as the Bazant Le Kirane paradox, and I state that this is the holy grail of mechanics and it requires a deeper understanding of the fatigue fracture of engineering materials and quasi-brittle materials. So the issue of fatigue fracture has introduced a new material length scale corresponding to cyclic loading. And resolving this paradox requires answering the questions. Are the length scale for monotonic and cyclic loading dependent on each other? And do the material microstructure govern the relationship between these two length scales? And why do we need to study this? It's not academic question. It is very practical thing which you need to answer, because in the HA code we have used this size effect factor lambda s square root of 2 by 1 plus d by 10, and this d 10 value is factor 10 is a transition length scale under monotonic loading, and it is usually a function of aggregate size. So as I was saying, the structures are subjected to cyclic loading also. So if you are not sure whether this d naught, whether we should use a cyclic loading uh, d naught corresponding to fracture cyclic loading or d naught corresponding to monotonic loading, and we don't know the relative sizes also, whether d naught corresponding to cyclic loading is higher than d naught or d naught corresponding to cyclic loading is lower than d naught. Okay, so without knowing that, if you use this equation, it's not exactly scientific. So we need to understand this. We have to resolve this paradox before we can use this equation. So resolving this PL paradox will give the engineers the correct transition length to be used in the size effect factor. Okay. So with this, I conclude my presentation. Uh, if you have fracture mechanics background, probably you would have understood a little bit. But anyway, thank you for giving me this opportunity to present and